Hello everybody. Today we talk about how to make a simulator of moon gravity so the astronaut can be trained in that environment. Okay, and so if you do that, you can tell how high the astronaut can jump up on the moon. And yeah, you can do that experiment, but you can also calculate using the physics. So that's what I'm gonna show today. Okay. The difference between Earth and Moon: Earth has a gravity g, and the Moon is 1/6 of g. And what g is 9.82 meter per second square. Right. So this is the acceleration, and Moon has 1/6 of gravity. How do we make that? The most popular way is to have airplane coming down, right? And what happened is this vertical acceleration is 5/6 g. This g is 1, so the remaining g you feel in the airplane is 1/6 g. Okay, so 1/6 g gravity you can make within the airplane coming down, but this airplane has to have this much g, and that means the velocity is going to be going downward. It's 5/6 g t. That means the velocity increase at this rate. So you cannot just constant speed coming down. This vertical speed has to be, if you draw like that. Okay, so you go up to say 10,000 meters, and coming down you can have like a minute or so the environment of 1/6 g, the moon gravity, right? But this is too short. 1 minute too short, and also very expensive, costly. You have to go up every time and come down, so and so, and the accuracy is not that good. So here's a very clever way to make it. This is a PhD guys considered. What we do is we hang this astronaut from the ceiling, right, and give a angle theta. Okay, so this gravity g we split into 5/6 g and 1/6 g. So this, you know, the sine theta is going to be 1/6. Such an angle, you hang it. Then what you do is you move this board over here and let him walk as a corridor from back of the this screen to the front of the screen, and this one is tied to the rail, and the rail move as he walk. So this rail going from the back of the screen to the front of the screen. So when he run, he experience 1/6 g, because the force acting here is only 1/6, and 5/6g is absorbed by this string, and he is standing on this corridor. Corridor is running from the back of the screen to the front of the screen. So he can walk, he can run, he can do all kind of experiment, and that's the way you can train the astronaut on the 1/6g. Now, wow, this is a very clever way to do it. After they do that, what do they find out? What they find out is you cannot walk on moon's surface. Okay, the ice is very slippery. Okay, but it's not smooth ice. Then you can still walk, and that's almost same experience as walking on 1/6g. The reason is, okay, this friction, if you have m, the friction constant is mu, mg mu is this friction, and for ice this is very small. Okay, but if m is 1/6, I mean g, mg mu 2, even you have a normal friction constant, because the gravity is 1/6, so it's almost as if 1/6 of normal friction constant. It's like it's rough surface ice. So walking is a challenge. You have to walk slowly, very careful. Okay, and jumping seem to go very high. So you are wearing the big space suits and the backpack. It's heavy, but still overall it's much lighter. So we calculate, see how much you can jump up on the moon. Okay, so this is how you do it. On Earth, we use this. When you jump, you use your legs force, and you suddenly use impulse muscle to jump up. Okay, and this is F, your muscle. Okay, so this is the physics same as impact equals mv. When you have impact, the mv, the momentum change, how much it's change. This is a formula, and if F F is almost constant for very short time of t, you can simplify to this. So Earth, you have F delta t, and that equals mv. Okay, and F is actually your knees muscle power minus your weight, which is mg, and this time m include the astronaut and everything, backpack, everything. So it's going to be right F minus, right, mg delta t, equals mv. If you remove this m by dividing it on both sides, it's become like that. Okay. But on the moon, on the other hand, the same astronaut has F, and M is the same. M is a mass, so it doesn't change. But this negative is not, it's weight. Weight is 1 over 6 g. M disappear, same way as this, equals v moon. And this is v earth. Okay? So this initial speed will be different by this factor. And when you have an initial speed, you know the height. mgh. This is on Earth, right? V square equals 1/6 mg height. This is moon. Okay, this much different, right? And this is gonna be mgm and mge. Okay, so generally speaking, the height is going to be this is going to be m disappear, so it's going to be bm equals ghm over 3. This is going to give us ve equals 2g he height over no, there's no over. Okay, so when you look at this equation, this one can be f minus g plus g, so it's gonna be, right, vm, which is gh, the height, jumping height on the moon, divided by 3. And this, what is this one, delta t, don't forget the delta t. The delta t, we move the delta t inside, so delta t times delta t and times delta t. Okay, so this is ve. So ve is this guy, so 2g jumping height on Earth plus 5 over 6 delta t equals ghm 3. Here you go. So this is the relationship between when you jump up, how high you can jump on Earth, and how high you can jump on the moon. Okay, so we want to know the height of the moon, so it's going to be hm equals g over 3, right? 2g h Earth g delta t. This g is here, and square. Okay, Let's plug in the number, see. Okay, when you are carrying spacesuit and backpack, say all of that is almost man's weight. So if you carry one man and jump up, how high you can jump on Earth? Say it is 10 centimeter, 0.1 meter. Okay, so 2 times 9.8 times 0.1 square root, right? Plus 6 times 9.8 the whole thing is square. Delta t, say when you jump up, you exert your knee muscle power for say how long? Say 0.5. Okay, and you have this in order to get the height on the moon. Okay, so let me run the calculator quick here. This is a challenging calculator. I'm gonna stop the video here and let me do calculation. Okay, I'm back. This part becomes 1.4, this 4.1, and this square, this whole thing becomes 30. And 30 times 3 divided by 9.8, 9.2. Okay, so if you jump up on the Earth 0.1 meter, which is 10 centimeter, it's about 3 inches, because suppose you're carrying very heavy stuff. Okay, then on the moon you can jump up 9.2, so 9.2 meter high. You can jump up almost 10 meter. Can you believe that? Okay, so the two things, the friction is very little, hard to walk, but when you jump up vertically, you can jump up 9 meter, no problem. And that's a kind of experiment the asteroid can do on this moon gravity simulator. And height 9 meter is a little bit high in this setup. This is a corridor. If you jump up 9 meter, this increase so much, so you can't swing too much. And this is tied to the rail, so it's move around. So in order to reduce this error, you have to make this very long. But in the facility, maybe from the ceiling, put the rail on the ceiling, probably is 10 to 20 meter is maximum height. So in the simulator, 9 meter high jumping, you may not observe that because of this problem, unless you make it ceiling very high, 100 meter, 100 meter, and let the astronaut jump up. So the 10 meter is not going to change too much angle, so you can get the close number. So when you do experiment, you have to consider this factor, right? But theoretically, you don't have any problem jumping up 9 meter. Okay, so that's today's conclusion. If you think this is very interesting, please subscribe and click like. The next space science subject is coming.